Welcome back to Collapsed Latents, this week in AI, where we cut through the noise and break down the most groundbreaking research in the field. I'm your host, and this week, we are diving into 5 papers that are redefining the frontier of generative AI, embodied intelligence, model security, inference efficiency, and fine-tuning strategy. We've got a lot to cover, so let's get into it. First up, virtual try-on. We've all seen the apps where you upload a photo and slap on a jacket, but in the real world, these models usually fail spectacularly. Extreme poses lead to blurry textures, and weird lighting causes identity distortion. It's essentially a failure of spatial and identity consistency. Enter Tstars-Tryon 1. This is a commercial-grade, real-time system from Alibaba, already serving millions on Taobao. This isn't just a research curiosity, it's a production powerhouse. Instead of relying on traditional inpainting, which often creates ghostly edges, Tstars-Tryon treats try-on as a multi-reference image editing task. It utilizes a unified MMDiT architecture, a multimodal diffusion transformer, capable of processing up to 6 reference garments across 8 categories, from tops and pants to bags and hats. The real heavy lifting happens in the data engine, which is built on image element decomposition and retrieval-based recall. After progressive resolution training and supervised fine-tuning on domain-specific data, they implemented a multi-dimensional reward pipeline using diffusion NFT. This uses reinforcement learning to optimize the model's policy by favoring stable, realistic trajectories. The result is a model that actually understands garment physics. It can follow complex instructions like wear the coat open to reveal the inner layer. In terms of performance, the jump is massive. While typical open-source models might take 200 seconds for a complex outfit, Tstars-Tryon hits it in 6.7 seconds. They achieved this via a streamlined 5 billion parameter DIT model, CFG, and step distillation. To validate this, they released the Tstars-Tryon benchmark, using a VLM-driven evaluation protocol to score identity consistency, garment fidelity, and physical logic. It's a massive bridge between theoretical research and real-world deployment. Now let's shift from fashion to physics. In the real world, agents don't exist in isolation, they collaborate and interact. However, most current world models are single-agent simulations. They're essentially watching one actor in a play, rather than the whole production. MultiWorld changes that. It's a unified framework for scalable, multi-agent, multi-view world modeling that solves the 3 biggest hurdles in the space: controllability, consistency, and scalability. It does this through 3 primary pillars. First is the multi-agent condition module, or MACM. It uses agent identity embeddings with rotary positioning, the same mechanism used in LLMs, to inject unique identity markers into action tokens. This ensures the model doesn't confuse the movements of agent A with agent B. Second is adaptive action weighting. Since not every agent is active at every single frame, the model learns to prioritize active agents and ignore static ones to focus compute where the change is actually happening. Third is the global state encoder, or GSE. This is the secret sauce. It fuses partial observations from all camera views into a single, 3D-aware global environment state using a frozen VGGT backbone. Because every view is anchored to this shared state, you don't get the geometry collapse or drifting usually seen in multi-view generation. The backbone is a flow-matching transformer with a frame-wise causal mask to prevent future leakage. They tested this on the multiplayer game, It Takes Two, and the Robo Factory Simulator, showing significantly lower reprojection errors and the ability to simulate failure trajectories, like robot collisions, safely. It can even handle long-horizon generation by feeding the last frames back into the GSE to update the state. It's a massive step toward truly embodied AI. Now, let's talk about a more dangerous side of the house. What if a single bit flip could destroy a state-of-the-art model? This is the premise of Deep Neural Lesion, or DNL. It's a data-agnostic, optimization-free attack that flips the sign bit of a few high-magnitude weights, causing the model to collapse. To understand why this works, we have to look at how weights are stored. Most models use IEEE 754 32-bit floats, consisting of 1 sign bit, 8 exponent bits, and 23 mantissa bits. If you flip the sign bit of a large weight in a first-layer convolution kernel, say an edge detector, you don't just tweak the value, you reverse its entire function. Because early layers are the most vulnerable, this damage propagates downstream. DNL uses a magnitude-based strategy, targeting the top K largest weights, while enforcing a one-flipper kernel rule to avoid cancellation. For higher precision, 1P DNL uses a single forward-backward pass to compute a hybrid importance score, combining magnitude and second-order Hessian approximations. The results are staggering. In ResNet 50 on ImageNet, just 2 sign flips dropped accuracy from 78% to 0.2%. In QN3-30B, 2 flips turned a highly capable model into a gibberish generator. This could happen in the real world via kernel rootkits, firmware exploits, or even rowhammer attacks that flip bits through electrical interference in RAM. The silver lining is that defense is possible. The researchers found that only about 1% of parameters are truly critical. By protecting just those specific weights with error-correcting codes or bit replication, they completely neutralize the attack. It's a stark reminder that deep neural networks are fragile and rely on a tiny set of high-magnitude weights, a single point of failure we can no longer ignore. Moving from security to speed, let's talk about large language models. We know they're powerful, but the inference cost is huge. The common solution is early exit, skipping layers for simple tokens to save compute. The problem is the KV cache. If a token exits early, it skips layers, but the next token still needs the KV cache from those skipped layers to maintain coherence. Most existing fixes are compromises. They either recompute, which is slow, or use rigid exit rules that hurt accuracy. River LLM solves this with a seamless exit framework. They introduce the KV shared exit river, a parallel path of lightweight, 4-bit quantized exit layers, specifically W4A16, that share the same addressing scheme as the full backbone. When a token exits the main model, it enters this river and traverses these shadow layers, which generate the missing KV cache as a byproduct. The model decides when to exit using state transition similarity, calculating the cosine similarity between a layer's input and output. If the state isn't changing much, it's likely an easy token and can exit. The results show a 1.7 to 2.1x wall clock speedup on Llama 3.1 and 5.4, with near lossless quality on GSM 8K and human eval. Because most tokens exit early, you can even use backbone offloading to evict deeper layers from VRAM, giving you a memory footprint similar to a fully quantized model while maintaining full precision when it's actually needed. Finally, let's look at the fine-tuning paradox. The standard playbook is SFT first for knowledge, then RL for polish. But in practice, SFT often causes catastrophic forgetting and collapses entropy, which actually limits the gains you can get from RL later. Group fine-tuning, or GFT, from the ZJU ACES lab, proposes a radical rethink. They argue that SFT is actually just a degenerate form of RL with a sparse, token-for-token reward. This creates a single-path dependency and can lead to gradient explosions when the model assigns a low probability to a valid expert token. GFT fixes this with two mechanisms. First, group advantage learning, or GAL. Instead of one expert answer, it builds a group of responses, including expert DMOS and self-generated samples, and computes a standardized advantage score. It's essentially contrastive learning, which preserves diversity and exploration. Second, they use dynamic coefficient rectification, or DCR. This applies a confidence threshold. If a token's probability is too low, it stops the gradient to suppress explosive updates while still allowing learning from moderately low probability tokens. The result is a unified, stable objective that blends SFT precision with RL robustness. GFT outperforms standard SFT on math reasoning and can achieve the same results with only 10% of the data. More importantly, because it preserves entropy, the subsequent RL phase has a much richer set of trajectories to learn from, leading to a significantly higher performance ceiling. Looking at the big picture, these 5 papers aren't just isolated wins. They're a glimpse into the next era of AI. Tstars-Tryon shows that real-world robustness is possible at scale. MultiWorld proves that multi-agent reality is a simulation we can actually build. DNL exposes a fundamental fragility in how we store intelligence. River LLM proves that efficiency and integrity can coexist. And GFT reveals that fine-tuning is a unified, contrastive process rather than a two-step sequence. The future isn't just about bigger models. It's about smarter, safer, and more integrated systems. If you're building or researching in this space, this is the frontier. Let me know in the comments which of these papers you found most interesting. Hit the like button to help us keep bringing you these deep dives, and I'll see you in the next one. Stay curious, stay critical, and keep collapsing the future.